Now in our previous video we solved some examples on the Laplace inverse transform of some functions, alright? And they were pretty simple ones. Now in this particular example, we'll be dealing with the inverse Laplace transform of this function, where the denominator here is just a quadratic function, alright? Okay, well, to do this, we need to split it into simple fractions by partial fraction decomposition, so that we can recognize their function, the original functions, alright? Okay, so I'll be working with this function actually, but let me just put this down. So the inverse Laplace transform of 1 over a squared minus 5, this is 5, this is a, plus 6, okay? Well, this is the same thing as the inverse Laplace transform of, well, the denominator here is factorable, okay? We can factor this and we will just have a minus, let's see, 2, then a minus 3, right? So by factoring this, we're going to have negative 2a and negative 3a. So you can take it like this, alright? Okay, so that is just it. So the next thing I would like to do is to split this, or to decompose this fraction to partial fractions, right? Okay, so I will be having that the Laplace inverse of 1 over a minus 2, then a minus 3, will be equal to the Laplace inverse of, now I'm going to say constant a and b such that this will hold, right? Such that we'll have that a over the first man, a minus 2, plus b over a minus 3 will give us the same thing, right? So the Laplace inverse of this right here will be the Laplace inverse of this. In other words, so that this and this will be the same. You know, Laplace transforms helps us to determine the uniqueness of a function. For example, no two functions have the same Laplace transforms. Okay, so to get these values of a and b, I would like to do this real quick using the cover-up method. So I'm going to go ahead and check which value of a will make this whole fraction, this first fraction here, to be undefined. And what we get there is that it is 2 that will make this first fraction to be undefined, alright? So I will just go ahead and cover that up in here, alright? Cover that up, then plug in 2 for a's, wherever you find a's, okay? So the idea is, what will make this fraction to be undefined? So when a is equals to 2, the whole of this fraction will be undefined, alright? Because if it's 2 here, we'll just be having 2 minus 2, which will just be 0. So we go ahead and cover that particular expression here, then plug into wherever you find a. So that will be 1 over 2 minus 3. So 2 minus 3 is just negative 1, right? So 1 divided by negative 1, the result is negative 1 for a. So we just do the same thing to find b. We check which value of a will make this whole thing to be undefined. In other words, which value of a will make the denominator here to be 0. When a is 3, the denominator there will be 0. So we go ahead and cover that particular denominator up, or that particular factor, okay, and plug in 3, that value, in here, and we'll be having 3 minus 2, which is just 1. So 1 divided by 1, that is 1. So that is the value of b, right? So here I can rewrite that as inverse Laplace transform of negative 1 over a minus 2 plus 1 over a minus 3, right? Okay, so from here, what I would like to do is to go ahead and split this, noting that one of the important properties of Laplace transform is that the Laplace transform of the sum of two functions is the sum of the Laplace transforms. That is to say, Laplace transform, yeah, it also works for the inverses as well. So that is to say, the Laplace inverse of this is the same thing as the Laplace inverse of negative 1 over a minus 2, and then plus the inverse Laplace transform of 1 over a minus 3. Alright, so that is just what I'm stating. Okay, so doing that, we get it very nice. Let me check this out. Alright, another thing we should know is that when we have the Laplace transform of a constant multiple of a particular function, then you just have to take out the constant. For example, you have the Laplace transform. It also works for the Laplace inverse, so I'm just using Laplace transform all the time. For example, if you have this, it's the same thing as a times the Laplace transform of t. Alright, to just factor out the constant, where a is a constant and t is the variable of consideration. Okay, so that is just it. So from here we can see that this will now become negative Laplace inverse of 1 over s minus 2, then plus the inverse Laplace transform of 1 over s minus 3, right? Okay, so that is very nice like that. Now, here is the deal. We know that the Laplace transform of e to the power 2t will give us this. So the inverse of this will give us that back. Okay, so we put that the minus e to the power of 2t. So you want to get it back as a function of t. So this is the minus from here. And the Laplace inverse of this right here will give us e to the power 2t. Alright? Okay, from the table, if you recall that, from the introduction of this inverse Laplace transform, so I gave that out, right? And again, if you just look at this, since this is negative 3, right? So we'll just be having e to the power of 3 here is what we will have here. So whatever is here minus that, so you just have it there, 3, and then we put down the t like this. So maybe I can just change things. This is equal to e to the power of 3t minus e to the power of 2t, and that right there is the inverse Laplace transform of 1 over a squared minus 5a plus 6. Right? Okay, so that has brought us to the end of this video. And please subscribe to this channel as you go ahead to solve another example.